Good morning, everyone. I'd like to welcome you to our CoCoRaHS WxTalk Webinar series. Today, we're going to start our broadcast here shortly. A couple of housekeeping rules just before we get started. Everyone will be muted during today's webinar, so we will have time for questions after the presentation. And so if you'll hold on to those till then, we'll ask you then to type in your question. Please include your state and name, so your name and your state with the question, and then those questions that we're unable to answer on the air, Karen will try to follow up with you via email afterwards. So if you see the little control panel on the right, go ahead and raise your hand. Go ahead, guys, and put your, there we go. We got our hands in there. That's great. And then under the question part, go ahead and type in your state. Go ahead, we'll see. We got a bunch of folks from all over the nation, and some familiar names that we've talked with folks in the past, and actually have met some of you guys. I see a gentleman there from Virginia that we met on the hurricane tour earlier this year. So great to have you all with us. Okay, we're going to start the broadcast here at the top of the hour very shortly. And stay tuned. We'll be starting that. Oh, hey, before I forget, at the end of today's webinar is a short survey. If you wouldn't mind taking that, just a couple of questions. Let us know how we're doing. Thanks. Okay, we're going to start the broadcast here. We're going to do our countdown. Here we go. 5, 4, 3, 2, 1. Hello, everyone. It's 1 p.m. Eastern, and that means it's time to begin our 66th CoCoRaHS WxTalk Webinar. A very warm welcome to those of you joining us today. I'm your host, meteorologist Henry Regis. Running the technical side of our program is our very own Noah Newman. We're coming to you live from the Colorado Climate Center here at Colorado State University in Fort Collins, Colorado. For those of you who are unable to join us for our live broadcast, we are recording today's talk, and it will be available later this week on our website. All of our webinars, there we go, are sponsored by generous donations from listeners just like you. Well, there was so much to go over during our March webinar regarding the Doppler on wheels that we've invited Karen Kosiba from the Center for Severe Research in Boulder, Colorado, back for part 2 on this interesting subject. Today, she will pick up with more about tornadoes, hurricanes, winter storms, and other high-impact weather from over a decade of field work. Well, Karen, welcome. It's great having you back with us today. I hope you've had a good summer. Do you have any interesting stories you'd like to share with us as we start things out from the past 6 months since we last spoke with you?
Hi, thanks for having me back. Interesting stories. Well, somewhere in my presentation, I might have a couple. We did some field work this year, which I will update everybody on at some point. But I have some interesting old stories, I guess, to share with people to start.
Well, great. Thank you, Karen, and you can take it away.
Okay, thank you.
Karen, really quick, we're seeing your more of your presentation form or format, and so it might be your other screen that would have the actual slide in a larger format. We're right now seeing you kind of more in presentation mode.
Hold on.
There we go. Looks good.
Okay, thank you. So thank you, and thank you for having me back. I really enjoyed doing the last webinar. The real awkward thing, so I feel bad, is I don't get to see anybody's face when I talk. So hopefully people still enjoy these presentations. So I wasn't sure how many people had been on the last webinar that are on this one. So I'm not going to repeat actually too much of what I talked about last time. There will be tornado and hurricane stuff in there. But I sort of am going to take over from where I left off last time and talk a little bit about some projects that people don't necessarily know we're doing, which includes winter weather and also looking at some other types of thunderstorms other than tornadoes. So just to get everybody started, and again, this is a little bit of a repeat from last time, but I don't know, you're supposed to hear things 5 times before you actually get them. So this will be the second time only. But just to sort of bring people up to speed on how some of the research works in atmospheric science. Really, you know, there's sort of 2 venues of research, and some people cross both of these and some people sort of stick to one. Myself, for the most part, stick to one, which is observations. And observations are really critical for understanding what we're seeing in models, what we're seeing in forecasts, what's wrong with forecasts, and what parts of the atmosphere aren't we observing and understanding. But once you get that information, working with models helps you with understanding, so you could model things in a really nice environment that you can't do when you go out and get observations in the atmosphere. And obviously models are really key to forecasting. So forecasting anything, you know, from small scale stuff like tornadoes, but even to large scale stuff like climate. So hold on one second, my dog is sharing my room with me. She was sound asleep all morning, except for when I start talking. So anyway, so between these 2, you really do still need to have an interplay. I'm not going out and taking observations of things we know and understand. I'm trying to get different and new observations of things that we have problems understanding. So I do a lot of my research with radar, and just to bring people up to speed, most people I'm sure are familiar with radar, but just a little quick information. All radars work the same, whether you're working with a research radar or if you're looking at your 88D radar. There are of course different qualities between, you know, a research radar and an 88D, or even a radar that, you know, your TV network would use. But radars, basically, I always think of them as flashlights on the atmosphere. So they're pulsing out some sort of energy, microwaves in this case, and they hit things that are in the atmosphere. They hit water, dust, grass, and then you get information back. So then you receive back that information. So sort of like an eye. If you're putting a flashlight in a dark room, the light reflects off stuff and you receive back in your eye and you perceive what's happening. So the same thing happens with a radar, and you could see what's in the atmosphere, but then you could also see how things in the atmosphere are moving towards and away from you. And that's what we call Doppler velocity, which is really interesting, again, for studying stuff like storms and winter weather, because you want to know how things are moving. But also really knowing what kind of stuff is in the atmosphere and how much of that stuff is what we call reflectivity, also gives you a lot of information. And these days, most radars are what we call dual polarization. So that means that they transmit information both in horizontal and vertical mode. And then that tells you a little bit more about sort of the shape or the size of the things that the radar beam is bouncing off of. So hail, snowflakes, rain, they all have what we call different dual polarization signals. And that's really interesting and really helpful because you can infer then what's going inside some of these clouds. So if you see one layer has snow and then you see below it that snow's melting and then you see big drops, you can understand a little bit more about the cloud processes, but you can also potentially understand a little bit more about how energy or heat is being distributed in these storms. So why use radar? Everybody, again, is, I'm sure, familiar with your 88D network, which is great for what it's supposed to do, which is cover the country. But if you're really trying to do research, if you really want to see what's happening near the surface, an 88D radar isn't going to help you very much. Also, if you're studying somewhat rare phenomena like tornadoes or hurricanes or snowstorms, the odds of it coming close to an 88D radar are very slim. We don't have that many 88D radars across the country, and they certainly don't provide the coverage for actually being up close to these different types of phenomena. So again, long time, you'd wait to actually get the observations that you wanted. So what we do is we put mobile radars, we put radars on wheels, and an 88D, again, is far away. So what two things happen? First of all, you're missing what's happening near the surface because both the Earth is curving and your beam is getting higher and higher in the atmosphere. And then also your beam starts spreading. So like a flashlight, your beam spreads farther and farther apart as you get farther away. And that means that you can't look at things in any fine scale detail. So a tornado, for example, you don't see a tornado with an 88D. You basically see what we call the hook echo, which is a very coarse resolution part of the storm that I'm showing up here. So by getting close, you get to see all of the stuff in great detail, and you get to see very near the surface. So an example here is that this would be your 88D radar looking at a storm, but then to the right here, this is what your mobile radar will see. So as you can see in the 88D radar, you're barely resolving this hook here, but in the tornado case here with the Dows, the Doppler on wheels, we're seeing a lot more detail, both in the hook precipitation field, but also in the velocity field as well. So again, closer really is key. It's not necessarily that much fancier. It's just being able to get really close to the phenomena that you're seeing. So for example, for us, when we look at tornadoes, this is what we're seeing. So this is a tornado that's less than a mile away from us. And you can see the eye of the tornado there. You can see this is the Doppler velocity field. And you can see all these small scale structures. You can see these other pieces of rotation, what we call horizontal vortices, rotating into the main tornado circulation. If you happen to have more than one radar, you could do a lot more science with that. So a single radar gives you something that we call Doppler velocity, and that's basically your movement towards and away from the radar. So it's not a true velocity, it's a vector velocity. So anything that's actually moving perpendicular to the radar beam, you're not measuring it because you need to have some parallel component with the radar beam. But if you have two radars looking at something and they're both looking from different angles, basically what you can do then is you could resolve the three-dimensional motion. So instead of looking at this Doppler velocity, which does have value and does mean something, you could actually put together a three-dimensional map. So you could look at updrafts and downdrafts, and you can look at how things move in the atmosphere more so than just looking at this field. And then you get something like this. So I always joke that you know everything once you have dual Doppler winds, but that's far from true. So this is an example of a tornado. So we've been looking at a lot of tornado Doppler velocity images, and you can see the difference here. So all these blues here, these are downdrafts, and this is what we call a rear flank downdraft or secondary rear flank downdraft. And then all these reds here are updrafts. So you're looking here at the gust fronts associated with a tornado. And then this is something called vorticity, which again, you have to derive that knowing three-dimensional winds, and you could say something more about the strength and the structure of the tornado. So not only do we work with radars, so not only do we operate 3 X-band radars, we've recently built, and I talked about this last time, a C-band radar, which has different capabilities and different advantages and disadvantages than the X-bands. One of them being, first of all, that it's a longer wavelength radar, which means it's easier to see through precipitation with it. But the disadvantage is that with a longer wavelength radar, in order to have the same resolution, you need a bigger dish. And you need to get down the road with your dish. So this radar, actually, we assemble on site. This dish comes apart in 2 pieces, but this also gets us the capability of better resolution. So unlike these, where we could just pull off the side of the road and start scanning any sort of storm, this radar actually requires about an hour or 2 of setup time. Other things that are interesting, radars give you a lot of information about winds. And like I said, you could sort of infer some thermodynamics, but really what you want is an array of other instruments and other measurements to tell you about what's happening. So sounding systems, we operate 5 sounding systems. We operate 5 mesonet vehicles, and these are basically cool vehicles with these masts on them that measure temperature and relative humidity, pressure, and wind speed and direction. And then we have an array of 20 weather pods. So these were originally designed for tornadoes, but we found them to be a lot more useful from other projects as well. So they're rugged. They're probably more rugged than they need to be for most of these projects. But the idea is that you can get a lot of thermodynamic and wind information very close to the surface over a large area. So we do all sorts of projects. I showed this last time, and I think right now we're sort of in a project lull, but I'll talk about what I think will be some upcoming projects. So a lot more than tornadoes, even though you can see there's certainly a concentration in the plains here of a lot of the projects that we've done. So with that not so brief intro, I was gonna start talking about snow, and it's sort of relevant, at least here in Colorado. It's getting chilly the last couple of days, and for Colorado, actually, we start getting snow in October. So I don't know if I'm quite ready for that. But this is, since everybody's different places in the country, this is not in Colorado. This is a project we did, Owls, over the Great Lakes, Lake Ontario, back a couple winters ago, looking at lake effect snow. So for those of you who are familiar with lake effect or not familiar with lake effect snow, basically in the winter time when the lakes don't freeze over, and you get these cold air outbreaks, so you get a lot of wind blowing over these somewhat relatively warm lakes, what you can get is you can get bands of snow that's set up right along the lake shore. So you probably hear a lot about Buffalo. Buffalo seems to be a great place for a lot of lake effect snow, and it's certainly a populated area. But another place that gets a lot of lake effect snow is sort of Syracuse, Oswego, and up into something they call the Tug Hill Plateau there. So there's a little bit of topography up there. And actually, amazingly, the Finger Lakes down here also can generate some lake effect snow. But the Owls project was focused on Lake Ontario and looking at the structure of these lake effect snow bands. So lake effect snow bands are more interesting than at least I thought they would be. So besides making copious amounts of snow in a relatively small area, they also have circulations in them. So something called Meso Cyclones. And this actually wasn't discovered until about 2012, that these small scale circulations existed in lake effect snow bands. And this is just an example. They look like cute little hook echoes, sort of in tornadoes. So you see that they have these little clear eyes associated with them. And then if you look over here in the Doppler velocity, you see that they have a little couplet associated with it. So you have some away from the radar and towards the radar. So this is a little circulation. And you have several of these that happen to form, in particular, lake effect snow band events. So just to give you an example of what it looks like, what a lake effect snow band event looks like. This is over Lake Ontario. This is reflectivity that you're looking at here. This is Doppler velocity, and you can see these vortices, if you follow my cursor there, along the edge of the band. So the band's sort of going through a bunch of different structural changes, and these vortices come and go, but eventually at some point, they all merge with the band there, and you can see that they move southward. So we were interested in understanding why these bands formed, why these misovortices formed in particular, and was there any enhancement of snow with them, and what sort of were the implications of these misovortices? So using our radars and using a number of other surface instrumentation, we set up a lot of different places. This actually took place December and January, so this is a 2-month project, looking over Lake Ontario and looking over these bands. So this is Oswego. This is the southeast side of Lake Ontario. This is Canada up here. There's also a Canadian component to this project. And again, we brought out sort of all our toys and started looking at what was happening in these bands. So this I'll just show quickly. This is those same bands that I just showed you in those loops there. But again, we had more than one radar out there, so we're able to do these dual Doppler retrievals. We're able to look at the 3-dimensional winds here. So what we see, this is all reflectivity, and these little circles here, those are vorticity. So those are all those misovortices. Those are all those rotations. And then this other black that you see here is updrafts, are all updrafts. And early on, you see there's not too much updraft on the southern edge of the band, but as the band becomes more intense, as you go later into the observation period, you see that there's a lot of updraft located here, and then there's a lot of misovortices that are strengthening as this updraft is increasing on the leading edge of the band here. And what you could do is you could look at these vortices, you could look at vertical cross sections of these vortices, and you could see a little bit more about how they form and what their characteristics are. So I'll just skip to that real quick. What you're looking at here is a cross section from south to north across those bands. And these black thick lines here, that's where the vortices are. And then these blue and white lines are what we call stretching. So basically that means that if you have some sort of rotation and you have a strong updraft, you could stretch it. And if you stretch it, sort of like the ice skater effect, what happens is that rotation becomes stronger. So we see that these vortices are located in a very strong region of stretching. So stretching, we're surmising, is part of their genesis mechanism. But where does this stretching come from? Where does this vorticity come from? This other thing, this white line here, if you see these white lines, are what we call shear. So if I was doing this in person, I'd have a pencil in my hand and rubbing my hands together. So if you sort of rub your hands together, and you could picture having a pencil there, basically what happens, you see that pencil starts moving and it's creating vorticity. So having that shear there, having your hands rubbing against each other, these changes in wind direction creates rotation. And if that rotation is located in a strong updraft, you start to get stretching, and then stretching increases the rotation even more. So these are forming in a region of this vorticity gradient, this shearing gradient, and then they're located then within a strong updraft. And then these they seem to persist. So in this case, what was the diagnosed mechanism for that was actually an Arctic front that was located close by. So how that got generated, was there was a front close by, but also within the band, there were fronts generated as well. So as these vortices are forming, they're also changing thermodynamic qualities. You're getting a little bit of melting going on, you're getting a little bit of refreezing going on, and basically you get some warming and cooling that's happening associated with the band. So the combination of an Arctic front pushing south with these bands actually generating some thermodynamic gradients is when these vortices form, sorry, I'm like vortexes, form. So,
Karen, let me interrupt you real quick. Just a quick question for somebody on the ground as these bands come across. What would they see? More intense precip there? Would they see a funnel cloud? What does that mean if you're standing underneath one of these vortices to the average person?
Yeah, so good question. So what I've been showing everybody is over Lake Ontario, and I was just actually about to talk about when they make landfall. So once they leave Lake Ontario and leave the sort of nice heating of the lake, they actually start dissipating. So you need to be right sort of very near the shore to see these bands and experience these bands. So it sort of depends on the conditions. So a lot of these end up happening at night, so you can't see anything. But what you get is basically a wall of snow that sort of moves towards you. So it gets really blowy and really blustery. And then it's over. It's a very short-lived phenomena. And if you look over the lake, some of these actually are associated with funnel clouds. In order to make a funnel cloud, just as a sort of little digression here, you need to have a moist enough atmosphere. So sometimes it's just not moist enough to make a funnel cloud, so they're not necessarily visible. But during this project, there were a couple times that people had seen these vortices on the lake and move onshore, sorry, towards our radars. So they're cool to experience, and they actually, again, since they happen in a very small area, can impact you when you're driving. It does become quite windy and you get whiteout conditions. And you get that more so than you would with just a normal snow band moving forward.
Would you get thunder snow or lightning at all in those as well? Or
so for this project, you're thinking of Jim Cantori.
Right. Yeah.
Yeah. So for this project, I think we only had one thunder snow event. And it was in one of these intense lake effect snow bands, but it only happened once in the whole 2 months that we were doing this. And this was actually a very active winter for us. This was 2013, 2014. So there were a lot of lake effect snow this winter. But yeah, getting thunder snow is pretty tricky to do. And that happens sometimes in these lake effect snow bands, but it happens more often in nor'easters or sort of medium cold type events, if that makes any sense.
Okay, thank you.
Yeah, no, you're welcome. I'm like, yeah, somebody's listening. It's so hard when I don't see anybody. But to be clear too, these Meso Cyclones, not that I want them to be tornadoes, but as much as I think, that they're tornado strength, they're not. So several of our radars and fortuitously a couple of those weather pods that we had actually have gotten hit by these Meso Cyclones. So this is an example of what it looks like in radar as it's just about to hit you. So if you weren't paying attention to the color table, you'd be like, ooh, cool, that looks, tornadic. But these are sub-tornadic strength vortices. So just to give you an example here, these are the strongest wind speeds measured by both the Dow radar and one of these pods, which is about 18 meters per second. 25 meters per second is what you consider a severe wind. So they're certainly windy, but they're not what you would consider severe. And even in terms of pressure drop, the pressure drop's a little meager. You get about a 1.5 millibar pressure drop. In tornadoes, for example, you get 20, 30, 50 millibar pressure drops. So these are not tornadic strength, but they are significant in terms of enhancing both snowfall and being, like I said, hazardous, sort of right along the shore of Lake Ontario. So keeping with the cold theme, another project that we did, so that project I just presented, actually that was one I had a lot of interest in scientifically, because once things rotate, I find them very interesting, even if they're subtornadic strength. But we also provide our radars to other scientists to do projects. And part of what I do is I provide my radar expertise in bringing these radars to a project. And this was a really fun project for me. It was called SNOWY, and don't ask me what it stands for. Don't ever ask me what project names stand for. People put a lot of effort into them, and then I never know what the acronym means. But the idea for this SNOWY project, basically it was looking at cloud seeding. So this took place in Idaho, in the Piatt Mountain Range, which is north of Boise. And what the scientists in this project were looking at how seeding, both naturally, so from other clouds, and man-made, so aircraft dropping silver iodide into the clouds, how that affected snowfall rate and then snowfall pack. And they had done a previous project in Wyoming called ASCII with one radar looking at some of this as well. But this project really took it up a notch in terms of where they deployed and how much seeding was going on during these events. And for people who don't live in the Mountain West, seeding, actually snow seeding is a thing out here. And certainly trying to assess the impacts of that is a big thrust, because our snowpack in the Mountain West really is what where our water comes from in the springtime and summer months. So understanding how that's created, or how maybe in an off year you could help create a snowpack, is certainly something interesting. Again, like I said, this is not my science project, but this was a really fun project for thinking about where to put our radars. So this, like I said, the radars, they had aircraft and they had all different stuff up there. Was in the Piatt Mountain Range, so north of Boise, near McCall, Idaho. And what we had to do is we had to bring our radars up 3 months or 2 months before the start of the project. So we put both of our radars on mountaintops, one of them called Snowbank and one of them called Pecan. And the only reason I mentioned the name is because one of them is called Snowbank, and I think in retrospect we should have thought more about what, why it was named Snowbank. But basically what we had to do is we had to drive our radars up these 4x4 roads. So here's an example of what the road looked like, and put them up there and get them all nice and set up in October. So we built little mud rooms. We snowproofed the radar pedestals, which really meant a lot of duct tape and tarp. We also wanted to make sure our radars were level. So we do have leveling devices, but we also found a lot of stumps out there to help keep the radars stationary and level. And we brought up porta potties, and we brought up, you can't see this here, but this is actually a living trailer for the people who are going to go operate the radars. So these were wonderful sites. The mountaintops, they had excellent visibility over the Piatt Range. But a little tricky to get to. So this is what we did in October. These are the two sites. This is the Snowbank site, and this is this Pecan site. And then this is the end of the project in March. So the reason I'm laughing at the Snowbank site is because we just did not anticipate how much snow they were actually to get at that site. So this radar, they just had to dig every day. Every day they were up there, they're constantly digging themselves out of snow. And then this is the other one, which actually didn't end up being so bad. So our operators had to snowmobile up for every time we did operations. So anytime there was a cloud seeding or a snow event going on, they'd basically snowmobile up to these radars, they'd often be there for 2 or 3 days because they're up there during a snow event. So they need for things to be cleared before they can actually get down. So they had about a 7 to 10 mile commute on snowmobiles up there. So the Snowbank site was sort of interesting in the sense that that was supposed to be a plowed road the whole winter because there's an FAA radar up there, so what you use for aircraft. And this huge snowplow, basically before and after every event, was supposed to keep this road clear. At some point during the winter, the snowplow broke irreplaceably. So it was a very tricky to get up there. We couldn't end up driving as much as we thought we would. And just to give you an example, a little bit what their life was like up there. Again, this is sort of during one of these snow events. You can see the radar basically over the snow hill here. And there was a lot of snow. So they had this little snow cave that they made to tunnel into their living trailer. And actually they had an 8-night stay at one of these radars during one of these events. It was a huge event. The snowplow was broke. It was very challenging to get them down. We were actually talking with Idaho Power and the Idaho teams to maybe get a helicopter or one of those snowcats up there to get them out. But eventually they ended up hiking down 7 miles to get back home. So yucky conditions, like I said up there, a lot of rhyming. So a lot of this sort of snow ice combination on our instruments. And as I mentioned, a lot of digging. So they spent a long time digging while they were up there, which is probably good. I think they would have gone stir crazy if they wouldn't. And just to give you an idea of the drift between January and March, so this is when, that's me, so I'm 5'5", just to give you perspective. That's when we got here in January. And then this was that same snow pack there in March. So this guy's probably, 5'11" or something like that. But it's a lot of him to get to the top of that snowpack. And then getting the radars down in the spring. So we had a tornado project that spring. This was a couple of years ago, and I was anxious to retrieve these radars so we could do our tornado project. And this was the end of March, and this is what it still looked like at the end of March up on these mountain ranges. So we took a snowcat up there. This is our nice snowcat road up there. As you can see, there's a nice cliff as well to get there. But basically, we had a snowcat up, and what we did is just clean out the radars, and we left them there to June and July. So they were up on that mountaintop for a really long time. It didn't, again, until June and July, we were able to actually finally retrieve our radars. So that was a good winter for them. It was a good winter for the project. And just to show you quickly some data that they got from the cloud seeding project, just so you can see a little bit what cloud seeding looks like. What you're looking at the radar here, this sort of whiter, sort of light green, light yellow stuff here. Those are the mountains. So that's what we call ground clutter. But then this stuff here, if you can see these little poofs, these little dots of poofs, that's actually the snow seeding plane flying and dropping silver iodide into the atmosphere. So you can see that actually you do get some return, some snow that's developing, but whether it lasts for a long time to make appreciable snowfall at the ground, that I don't know. Again, I wasn't a scientist on this project, but if you actually are interested in reading about that, let me know and I could sort of direct you to the people who did this project and what they're finding. I just thought, like I said, it was sort of a fun project, just snowmobile up to these radars and, have to deal with sort of an extreme condition and figuring out what to do. So that was my snow part of the talk that I never got to last time. So got you in the chilly winter mood. But then I'm going to switch now into warm season stuff. So I'm going to talk a little bit about something that we call squall lines and MCSs. This is kind of the part 2 random stuff that we do with the radars talk. But again, these are all sort of really fun projects and they just don't necessarily get talked about as much as some of our tornado projects. So this project was called Pecan, and this was a project that I was interested in as a scientist, so switching back to something that I'm also looking at the science for. And this was looking at thunderstorms that happened at night. So thunderstorms in Kansas, Nebraska, Oklahoma that happened in the evening. So what happens a lot of times is that during the day, in these different places, you get sort of what you think of as, tornado producing or ordinary thunderstorms, where you get these big cells that go up, make a lot of rain, make a lot of hail. But then as you transition to the evening, what ends up happening is after all these storms go up, they start interacting with each other. And then what you get is this big storm complex. And we call those MCSs, or mesoscale convective systems. And mesoscale convective systems are responsible for a lot of the rain that the plain states get, and even east of the plain states, because they're just big rain producing storms, or big storms. The other thing that they can do, and this is more in my wheelhouse, is they could have really strong winds associated with them. So maybe you've heard of bow echoes or squall lines, or even in an extreme case, a derecho. Basically what happens is these storms, even though they're very linear and long in structure, they develop really strong winds behind that. So they get what's called a rear flank, or sorry, not a rear flank, a rear inflow jet that penetrates down to the surface and can cause a significant amount of damage. And it's actually a really hard forecasting problem because people look at the 88D radar, the weather forecasters, and they see these structures that look like they could potentially be making severe winds at the surface, but they're looking at the winds above the surface with these 88D radars. So they don't really know if these strong winds are actually making it down to the surface. So
Karen, just to interrupt you one more time, just a question probably our viewers are thinking about with these MCSs. You mentioned a lot of tornadoes and stuff with the supercells before that, then they combine it to the MCSs. When these bow echoes come and so forth, do they have tornadoes contained in them, or are they more just straight line winds when they move across? So what is?
No, that's a good question. Yeah. So two things. So yeah, first of all, I always laugh. This project was, for myself and for a bunch of people who do tornado stuff. Basically, we watched all the tornadoes happen from our ops center, and then we went out and deployed them on these, things as they grew, what we call upscale. So they have both associated with it. What they're really known for are really strong straight line winds, and that's predominantly the risk from these. They can have tornadoes associated with them, and one of the ones that happened during our project did, but they're usually very weak. So you almost couldn't even tell the difference between the tornado happening and the straight line wind event. And you probably should be more worried about the straight line wind event than the tornado event. And these things also, just as a side here, for people who follow tornado projects, there's a project going on called Vortex SE right now, Vortex Southeast, looking at tornadoes in the Southeast United States. So Alabama, Mississippi, I'm trying to think of Southeast states, so like Alabama, Mississippi, and even though they get supercells in those states, really what they get a lot of are these MCSs, these quasi-linear convective systems. We have about 1 billion names for them.
And how fast are these winds? So when people hear straight line winds, are we talking, tropical storm strength, hurricane strength? Is it at 50 miles an hour? What are these winds like?
Yeah, so they are, and I'm just going to do a quick conversion to make everybody think in real units. So they're in excess of 55 miles per hour. So 55, 60, 70, 80 miles per hour are usually the strength of these winds. So our criteria for severe winds, just meteorologically, is 55 or 56 miles per hour. So anything above that, we classify as a severe wind. And the idea with that classification is that at that point you could start getting damage. So you could start getting, tree branches down, damage to structures. And that also coincidentally corresponds with a little bit of how the EF scale also is derived. So yeah, so you're talking winds that could do damage and over a large area. So tornadoes, for example, obviously can have much stronger winds than these straight line winds, but you're not necessarily looking over a larger area with tornadoes. Straight line winds with these systems could actually impact a lot of different places at once.
Thanks.
So yeah, like I said, I mean, the real big question is actually predicting these strong winds. Is really a forecasting challenge. So again, we took all our tools out to this project, and like I said, the amusing thing about this project was, everybody's like, but there's tornadoes happening now. I'm like, yeah, no, sit there, wait. We're waiting for what happens after the tornadoes. So every good project, and I say this facetiously, but I said that the project was basically, Oklahoma, Kansas, Nebraska. And as what happens is the severe weather occurs outside of what you consider your project domain. So even though we were sort of based here in western Kansas near Hayes, a lot of the severe wind events happened in Iowa, South Dakota, and Minnesota. So a bit outside of where we were planning on studying, which took a lot of driving to get to, but definitely worth it. So these are the severe wind outlooks from the SPC, Storm Prediction Center. Each of these cases, Illinois, South Dakota, Minnesota, they all had a big risk for severe winds. In particular, this day in Minnesota did, as well as this day back in Iowa. So I'm just going to talk really quick about Minnesota because I never think I'm going to talk that long, and suddenly it's 40 minutes later. Because this is an interesting case, this really had a strong outlook for severe winds. I was really excited for deploying on this case. Just like tornadoes, once things become hatched, that means we're serious. Something, there's a good probability of something happening. Once we move outside of our domain, it's obviously a little challenging for us to deploy. The one thing with radars, and I sort of showed you this a little bit in Snowy, think of radars almost as, what you could see with your eyes. So if there's hills or mountains or trees in your way, you're not going to be able to see a lot with the radars either. And in this case, in Minnesota, and then this is Wisconsin, and this is a river, the Mississippi River, there's a lot of rolling hills there. So it wasn't necessarily the best place to put a radar, but it had the best forecast for these severe winds. So to give you an example, this is what these storms look like. These are what these squall lines look like. And this one is bowing out. So it starts to really, the front part of that really starts to become sort of U-shaped. That's usually when you think the severe winds are going to start occurring. This white square here is where we put our assets, so a little bit south of this bow, but certainly within a region that you would expect to get severe winds, both given the forecast and given the observational radar presentation. And what I classify these winds as is plastic lawn chair tipping winds. So despite this forecast, despite this outlook for these severe winds, for a large portion of the storm, the winds were never severe, and they certainly were not severe where we were measuring them. So 18 meters per second, I sort of put this line in here, even though I said 25 is actually what you really want to consider for severe. You can see the red is the wind speed. It barely even gets up to the 18 meter per second criteria, anywhere within our observational domain. And I look for severe winds a lot. So if you look at the radar observations, there are some places slightly above the surface where you're seeing winds of almost severe criteria. Like I said, 25 is severe criteria. So I guess that one technically makes it, and that one technically makes it. But certainly not what was forecast. Certainly not this, hatched wind outlook at our location. And again, these hatched wind outlooks are over a large area. So a lot of people in this area are getting warned for severe winds. And then when you look at the severe wind reports, this little yellow here is where we were. You see that they're, first of all, it made a tornado initially early in its life cycle. But then in terms of severe wind reports, there are some, but really they didn't start happening until, eastern Wisconsin and northern Illinois there. So a bit to the east of what was really forecast for the severe wind probability. And to sort of lead up why, and again, I know I'm skipping through a lot, the problem ended up being in this case, and it's difficult to diagnose, is that right here, if you look at where my arrow is here, is that the shear vector, so how the winds change speed and direction with height, actually wasn't very favorable for the severe winds to happen. So even though you had a really strong bowing segment there, you saw that, the winds behind that, or sorry, the temperature behind that actually was quite cold. So it was actually quite cold compared to the environment, and that's usually a good thing if you're trying to get severe winds in these storms. But really the failure mode in this case, we think, is the orientation of the storm to the environmental shear. So again, at some point, presumably the storm and the shear vector became better oriented, but during the parts that we were observing it, it wasn't. So how this translates into forecasting obviously is a tricky thing because this type of information, of course, is not available to forecasters. So really trying to diagnose this with observational data is something that we really need to work towards. So again, this is an example of this Pecan project. And then I'm just going to segue into a couple other random things that we look at with radars. And this one has no place anywhere. I was looking at the Eclipse, but it actually ended up being pretty interesting. So back in 2017, which I'm sure people remember, we had the Great American Eclipse. And we thought it might be fun to take our radars out and see what we saw during the eclipse. So we brought 2 of our radars, we brought a bunch of our other instruments up to Wyoming. It really wasn't that far for us. And we didn't necessarily have any huge objective. We expected it to get cooler. We weren't really sure what we'd see with the radar. We thought, I don't know, maybe something interesting will happen. And again, it was close, so why not give it a try? It's sort of an interesting phenomenon. You're turning off the sun and then you're turning it back on. So I don't know what could possibly happen. So again, a lot of people are sort of asking us, what are you looking at? Like, I don't know, we're gonna look. So what we did in order to make this sort of a very nice, easy experiment and maybe something that people could use for teaching is we found an area in Wyoming that the eclipse was the totality of the eclipse was going to happen that was relatively uniform. So we didn't want to find somewhere where it was hilly or had a lot of shrubs or there was a lot of change in terrain, because everything that we measured, we wanted to make sure that it was actually due to turning on and off, the sun, not because of a hill or because of trees or something like that that was affecting the underlying surface. So we found the most boring part of Wyoming that was in totality, and we put all our assets out there. We also launched soundings. Again, we were just sort of in fishing mode here. But it ended up being quite interesting. And every time I show this at a conference, nobody's really jumped on this data yet, but everybody's sort of like, oh yeah, that is cool. As you would imagine, the temperature got colder. So this is temperature from our surface measuring instruments. So you see they're all, sort of 0, and then they change about 7 degrees during the passage of the eclipse. And the wind speed too. So this is wind speed, you could see. You see that the wind speed actually, as the eclipse is occurring, starts to drop off. And then it takes a while for it to recover. So we thought that that's sort of an interesting result. Again, this is kind of a random why did you do it thing, but it's also interesting because it is showing a lot of variability. So this gray line here, this is where totality, maximum eclipse was occurring. You could see obviously the temperature is dropping before that as it's partially eclipsed. And you could also see correspondingly the wind speed start dropping before that. And then it takes again a while for both the temperature and the wind speeds to recover. And if anybody went out and saw the eclipse, I'm not sure, and I can't ask you really if people did, it was really bizarre. It did sort of get quiet in terms of the wind speed. It just, everything sort of just went nice and silent. And
you know what we'll do, Karen? We'll ask everybody if you'll raise your hand if you saw the eclipse. We'll get and there we go. Yeah, we got folks that did. So
yeah, so I mean, for everybody who was out there, I mean, I'm sure you remember that. It was really eerie. I mean, besides obviously the fact that it got dark, the wind really just calmed down sort of as the eclipse was occurring, and then it sort of resumed normalcy, half an hour or so after that. In terms of what we saw with the radar, I think this is also interesting, and it's sort of mimicking what we saw with our surface stations. So what you're looking at in radar here is what we call clear air. So what you're looking at are a lot of bugs, and you're looking at dust, and you're looking at other kind of fun clear air stuff, grass, whatever happens to lift up during the day. So you see here, you're seeing a lot of return, you're seeing a lot of yellow. This is velocity over here, this is reflectivity. You see that eventually it kind of starts lining up. You get what we call these boundary layer rolls, which is typical of a boundary layer. And then as you see, as the eclipse is occurring, the boundary layer goes away. You see how that yellow goes away, and then it starts recovering again. So just like we're seeing in the surface observations, the radar is actually also showing the boundary layer nice and healthy. And then as the eclipse is occurring, the boundary layer collapses, and then it starts becoming interesting again. The other thing that we see is that if you look right here, a little boundary develops. So right here, and you can see that in velocity too. So some boundary develops and actually moves through what we're looking at with the radar right after the eclipse. Again, this is sort of just a fun, cool thing. I always feel like I need to show it, but I never really know where to show it because it's like, oh, and then we looked at the eclipse. But there's a lot going on here, and I think actually at some point this would make a really cool teaching tool for people. So what's 2019 and beyond? I know you asked this at the beginning, but I saved it all for the end because 2019 was a quiet year for us, but we got, I'll say, a lot of work done. We also did do a couple of deployments. So I'm gonna switch back a little bit to tornadoes because every year we try our hardest just put aside a couple of weeks in the spring season to try to go out and get tornado data. The reason being is because tornadoes are rare phenomena. So in order to get the data that we want, it's sort of like you just have to keep trying to do it. So the more you're trying, hopefully you start getting and compiling data that you want. And in particular, we have a really rare set of data that we're trying to obtain. I think we're the only group really doing this, is that we're looking at trying to get data very, very near the surface, both with our radar and then also with getting surface instrumentation in the path. So I had this, I presented, these sort of motivation slides last time, but just to, again, I don't know how many people were here from last time. But the question is how do tornadoes do damage? And I know everybody's like, well, they're windy. That's how they do damage. But really what we're trying to figure out is what are the wind speeds like and what are they like near the surface? Because are they changing speed with height? Are they changing direction with height? Is that what is that how they're doing damage? The change in speed, the change in direction? How fast do these winds fluctuate? And relate that to what you see with an 88D radar. So again, with these 88D, with your observational radar, you are definitely not looking at anything near the surface. Like I said before, you're barely looking at the tornado if you're lucky. So really, we're just trying to figure out this profile to work with engineers, to work with people who are studying damage from an engineering perspective, so they could properly model how these tornadoes are doing damage. So we had this really, really fortuitous observation, and I probably told this story last time because I always do when I show this. And if you look, this is height, and this is what we call, it's just a non-dimensionalized velocity. So basically 1 being that this is matched at 10. So everything below 1 means that the winds were stronger than they were at 10 meters. And 10 meters is just basically your standard observation height. I don't really know why they use 10 meters, but it has been, and that's what's being used. One of our Mesonet trucks and our radar got hit by a weak tornado. So this is a data set we don't ever think we're repeating. But what we find interesting here is that as you see, a lot of the strong winds, and these are all just different times in the tornado life cycle, at a lot of times, the strongest winds are occurring below 10 meters. They're occurring below rooftop height. And if you look above 10 meters, and there are some exceptions, these are where the winds aren't as strong. And these are where you commonly get observations with your 88D radar. So what this implies, at least in this tornado, is that your strongest winds are actually not being observed and are happening very close to the surface. So we put instruments out every time. This is another example of us trying to do this. These wind barbs here are not a Mesonet this time. They're actually a pod, so an unmanned vehicle. And you can see that you're seeing the winds and how it relates to where the tornado is. And in this case, and these are sort of weird units, the yellow observations here, the yellow dots, those are all what we're observing with the pods. And then this is what we're observing with the radar. But in this case, what we're seeing is the winds with the pods, so the winds at 1 meter, not at 3 meters, are actually about 50 to 70% of what we're seeing with the Dow. And then the other case that I just showed you, those were winds that starting at 3 meters and above. So as you probably would expect, the winds at 1 meter, you're getting close to the surface, you're getting close to where things should be 0, are getting reduced from what we're seeing at, say, 30, 40, 50 meters above ground level. But what we're trying to do is we're trying to get more than just these case studies. So I sort of showed you my two best tornado obs. But what we actually have in a lot of this is we have a lot of different observations that don't necessarily meet this criteria, but give us some information about what's happening below 100 meters. So looking at our entire data set, and I didn't include this year, and I'll tell you why in a second, between 1995 and 2017, there were 23 cases that I found that have observations, or at least one observation, but preferably more observations below 100 meters. And in that case, 30 to 30% of these observations have the strongest winds and their lowest observation level. So we're finding that really interesting, that it really seems that we're not capturing necessarily the strongest winds in our observations. And I could go through and show you a bunch of all these. This is what I've been working on in the last couple of years. But in terms of 2019, so this was this year, and we were trying to get more of these types of data sets, both to hopefully get, you know, the holy grail of it, but also to get more to put into our climatology. We don't go out that often in years that we're not really funded to do projects. We sort of go out and do radar testing, but we do them near tornadoes. So we're based in Boulder here. This year we went out McCook. Then there was a day down in Oklahoma, Mangum, Oklahoma, that we sort of intercepted 2 different tornadoes. So this is this Mangum day. I keep wanting to call it Magnum, Oklahoma. Mangum, which, if you're a tornado follower, you probably saw that there was a lot of chaser convergence on this day. This was the day, and I'm trying to look at the date again, but whenever it was, that they had the, you know, super high risk day that every model said that there was going to be tornadoes blanketing the states of Oklahoma and Texas, which of course did not happen. But there obviously were some significant tornadoes that occurred. Unfortunately for us, and if you do chasing in Oklahoma, you'll find this out pretty quickly. Chaser convergence is a real thing. So we could not really get to the tornado because of all the traffic there. So we were a little bit farther than we wanted to, and this is actually data that I took while we were moving, while we were driving, while we were trying to get to the tornado. But this is an example of what this tornado looked like. So here's this reflectivity. You can see the clear eye there. Here's the tornado. This is something we call this rho-HV, which people use as a signature for debris in tornadoes. And this is just the evolution as a tornado versus time. And you see in this last one here, you see what we call a debris ball. So you have really high reflectivity, and you have really low this rho-HV, cross-correlation coefficient, meaning that the tornado is wafting debris. And when I say debris, I just mean a non-meteorological scatterer. So it doesn't necessarily mean, you know, bricks and wood planks. It could also just mean a lot of dirt and leaves, and sort of bigger things that aren't, you know, raindrops in this case. So unfortunately for this one, we measured winds of over 150 miles an hour in this tornado, but we are moving for most of our observation period. So the other one that we did was this McCook tornado. So that was the one up in Nebraska. And I'm showing a sort of really messy plot for a couple of reasons. First of all, that we're just starting to look at this data. So we're really good, I think, at deploying near where tornadoes form. It's something that we do really well. So this one formed, I guess, a little too early. We were hoping that it would form a little bit farther away from us, and that would go over our pods. We'd get great data, we'd move on, collect some more. But unfortunately, it kind of formed right where we had deployed our instruments, including our radar. But we were still able to get information. These are from these different surface pods, those yellow pods that we're dropping, wind barbs, and then something called theta E, which is potential temperature, which tells you a little bit more than just temperature. It tells you a little bit more about the buoyancy of the air surrounding these tornadoes, which is more meteorologically interesting than just temperature. But you can see, in particular, this pod B and this pod D, we got pretty close. Again, what we really want to do, though, is get these pods, you know, like here. But this is sort of, you know, the thing that ends up happening with pods. So that's why we have 20 of these, really trying to increase our odds. So what I've been starting to try to do is not just look at the winds surrounding the tornado, because we have a lot of misses with these pods, but also look at some of the thermodynamics. And for those of you who were on the call last time, you might recall that I talked about sort of I'm going to say temperature, but what I really mean is buoyancy of the air surrounding the tornado. So there's this idea out there that you could predict tornadogenesis, or you could have an idea if storms are going to make tornadoes based on the downdraft temperatures surrounding the rotation surrounding the mesocyclone, and how that compares to the inflow air. And these plots are not pretty, and they're not necessarily made to be read. Again, I've really just started this a few weeks ago. But since we don't have these low-level wind observations exactly in the places we want them for tornado wind structure, it doesn't mean that we can't get a lot of information about the thermodynamics. So looking at these downdraft temperatures or these downdraft buoyancies and how it relates to the inflow and how that evolves versus time. And also then just relate that to storm structure. So looking at not just the tornado in really fine scale detail, but looking at these downdrafts and these updrafts and these fronts that surround it. So when I started reducing, not necessarily focusing on just tornado observations, we have a number of these cases where we didn't get what we wanted for that, but we got thermodynamics and storm structure information in these variety of different storms. So that's one thing that we're looking at. The other thing we do a lot of is hurricanes. Again, these are things that are sort of close to my heart. And I haven't put Dorian on here yet because I'm not really sure how I want to count it. So in hurricanes, what we're doing is we're not looking at the large scale structure in hurricanes. What we're looking at are these boundary layer roles and these boundary layer structures in hurricanes. So you think of hurricanes with big eyes, but really we're only looking 5 or 6 miles out into a hurricane. And we're trying to quantify what's happening, sort of like in tornadoes, what's happening really near the surface in hurricanes. So this was from Harvey, just to refresh your memory what it's like to be inside of a hurricane. It's windy and wet. Hurricanes are probably the most visually uninteresting meteorological phenomena, but they're interesting in data-wise. So again, just sort of showing you, the scale of a hurricane. And we're really looking at this really tiny part surrounding the eye. So we're really looking at a very, very small scale phenomena. So as everybody I'm sure is aware, Dorian was occurred about a month ago. And Miami, Florida is probably, our worst case scenario. Again, we're based in Boulder. So that's, a 3-day drive for us to get all of our vehicles out to the coast. So we have to make a decision quicker than we normally want to make a decision. What we like to do is wait a little bit. So if it's making landfall in Texas, for example, we can get a better idea of where the track's going to be and whether it's not, it's going to make landfall as opposed to places like Miami and places like Wilmington up there. So this was the forecast when we had to make a decision on whether or not we wanted to deploy our radars down in Dorian, so this top left panel. So as you can see, this is Thursday morning, and again, this is sort of when we need to make our decision. The track of the hurricane, and I can show you all the spaghetti plots too. Basically, it was forecast to make landfall around Fort Pierce, Florida here as a major hurricane. So we decided to pull the trigger. We decided to drive all of our vehicles down to the coast. My colleague and I flew out in advance of the vehicles because what we do is we basically survey within this cone where the hurricane's gonna make landfall and try to find places to put our radars. And it's tricky because what we're trying to do is we're trying to get as close to the ocean as we possibly can because we want to see what the winds are like over the ocean, but then we also want to see what they're like as they make landfall. And there's a lot of flooding, there's a lot of strong winds that are happening. So we're trying to find a place primarily that we think, isn't going to go underwater. So it takes a lot of time, and especially in some place like Florida, where it's pretty much all sea level, to find locations for our radars that we think are suitable for our objectives. There are other groups that go out and do hurricanes, but they deploy a little bit farther inland than we do because they're more interested in looking at the larger scale structure. So again, we're sort of a unique group and have a unique challenge in placing our instruments in these things. But anyway, this was the forecast on Thursday. Friday morning, we woke up in Florida surveying. That was the forecast. So we were actively surveying for sites in Florida. Major hurricane again, forecast to make landfall just north of Lake Okeechobee there. And then for those of you watching the news, I'll say there's a little bit of Alabama. We saw that this track started changing. And actually, it's a pretty confident move for the Hurricane Center to make to actually keep it offshore because obviously there's a little error there, but also big implications in a case like that for this error. But again, the fact that they moved it offshore and again, looking at models, really makes you think it's not going to make landfall in Florida. Unfortunately, our trucks, are about in Mississippi at this point, and we had spent several days surveying the coast, looking for that. Unfortunately for us, not unfortunate for the people of Florida. Very good. That's always a good thing. But the forecast again became more confident that it wasn't going to hit Florida, but it also was starting to potentially hit the Outer Banks of North Carolina. So we had a decision to make at this point, whether or not we stayed down in Florida. We were down here and sampled a major hurricane, which might have strong winds that we're able to see with our radars from the shore, or drive up to potentially the Outer Banks, resurvey, and have a storm that's potentially a lot weaker than what we could sample down here. So we decided to stay down here and sample. Again, this is very good for the people of Florida, and I'm not hoping to take data in a major hurricane, but if it is making landfall, obviously we do want to be there. So this is what we saw with our radar. What you're looking at here are RHIs. So instead of doing a horizontal slice through the storm, we're doing a vertical slice. And these little pieces here that you see of yellow reflectivity, those are just different rain bands moving towards the radar. The eye, in this case, though, was at 120 kilometers out here. So about 70 miles away from us offshore. So you're not really seeing the eye, you're seeing the edge of the eye wall at some points in this area. And like I said, the rest of this moving forward is rain bands. But even though it didn't make landfall, there actually is a lot of interesting things going on, even if you're not studying winds. And it's a little hard to see in this loop, but you can see the melting layer. So if you see this dark part here, it'll come up soon, the sort of dark brown reflectivity that comes up. So that's the melting layer in there. This is velocity. So there's some interesting velocity structure happening. But really, I think what's happening that's really exciting is sort of the precipitation physics that's happening. So this melting layer, and then this is rho HV. You can see it in this field as well. There you go. Then also the secondary field here, it's called ZDR, which also tells you something about the precipitation physics. So not looking at winds in this hurricane, again, this is sort of fresh new stuff, what I've been doing. There's, I think, a lot of interesting precipitation physics that people could start looking at and looking at some of the processes of rain formation in these different storms. So that's what I've been up to since the last time. I certainly have a lot more stuff I could talk about, so I'm just going to actually just do one last thing, and then I promise I'm done. We're hoping in 2021 to do a project called Langostino. And again, here's your horrible acronym. Basically, we've been proposing this project for many years, and it's to look at nor'easters. So much like I showed you way at the beginning of this presentation for this OWLS project, people actually have not really looked at mesoscale features, so these bands, vortices, boundary layer structures in nor'easters. So people a lot of times are looking at the giant nor'easter storm, the giant parts of these storms, but they're not really peering into the small parts. So we thought this would be a great time to do that, to do a project like that and look at improving forecasts, in particular looking at precipitation forecasts and location and timing of small scale structures in nor'easters. So things like coastal fronts, which can affect whether or not you're going to get rain or snow, mesoscale banding, which can affect how much snow you're going to get, are all things that are hard to predict and a little bit unknown in terms of precipitation physics. So here's our proposed domain. We're proposing to base just south of Boston, which is nice because it lets us get out to Cape Cod pretty easily. We're also proposing to put one of our radars out on Nantucket Island. So I'm not really sure who's going to volunteer for that yet for the winter. But the idea of doing that is that you get a lot more radar coverage over the ocean. So even if the nor'easter misses or sort of skims the coast, you're still going to get some information about what's going on. And the other exciting thing with that, and I'm just going to click forward, is that NASA is doing a project the same year. So in 2021, NASA is going to do a project called Impacts, and they're going to fly a lot of their NASA things, not rockets, but they have a lot of planes. So they have this ER2 plane, which flies up really high in the atmosphere. They have a P3, and then they have a couple of surface observations. But the idea really is that NASA will be providing the planes for this project. So they'll be flying through the bands and the nor'easters, but we're going to provide all of these different surface obs. So we're proposing our 4 radars, we're proposing to do about 800 soundings during a winter period, and then also looking at precipitation rates and water content in these nor'easters. So that's really it, I promise. That's what we've been working on, and that's hopefully what we're going to be moving forward with in the next couple of years.
Well, Karen, thank you so much for coming back. Really appreciate really good stuff. A lot here. And folks, if you're in this area in New England there, your CoCoRaHS observations, I'm sure, will be helpful for the precipitation measurements during that time as they do this project. So, yeah, I'm looking at just at Connecticut, Long Island, parts of Massachusetts, and we have actually a school out on Nantucket.
Oh, that would be awesome.
Yeah,
so if you're
that
on
would
there,
be neat. Yeah.
Yeah, do talk to me. So I didn't really mention it too much yet, just because we're still in the it's getting reviewed process, and I'm trying not to be overly optimistic. But if it does get funded, we're really looking for a lot of community science to take part in this project. And we're going to be reaching out to local communities. We're going to be working with the Boston National Weather Service. So if there's schools, there's people out there that are interested in taking snow obs, for us, we'd really be very interested in coordinating with you.
So Karen, get in touch with us as we get a little closer to that time.
Yeah.
That'll be great. That would really be wonderful. Well, folks, we're going to ask you if you have any questions now. We have a little bit of time left. We're not going to take too many right now, as it's about 10 after the hour. But if you have a question, go ahead and ask it. I'll tell you one quick thing. I was just recently down in Mexico City talking to the folks down there at their National Weather Service. We are so fortunate in the U.S. They only in the whole country have 9 C-band radars, and only 4 of those are operational at this time. So we just have we're so lucky with all of our weather service radars and the information that we're able to get and help these experiments out and so forth. Okay, here come the questions. So here's one from Tommy in Virginia, and he was wondering, does your group take college students on any experiments? I'm sure there's folks interested in that, and is that open to college students?
Yes, we most definitely do. And again, I think this Langostino project probably will be our next one. We definitely do. We're just not as organized as probably we should be. So if people email me, depending on what project we have, depending on what we get funded, we're always I pretty much want to say we're almost always looking for participants for these projects.
So we'll put Karen's email up on the website after the talk today. Here's one coming from Sean, and he wants to know any correlation between Meso Cyclones and physical placement on the lake. So perhaps suggesting static warm currents in the lake. Curious about that.
Yeah, no, that's a very interesting question. And actually, a colleague of mine is working on some of that. So I'm going to give you a wishy-washy answer since it's still in development. But again, a really good question. So there's 2 things that people are looking at in terms of placement. One of them is the interaction with the shoreline. And if that impacts both their placement and then also how they're oriented within these bands, so how these vortices are oriented. And then the other thing people are looking at is what we call a lake-to-lake connection, and basically looking at upstream influences from the upstream lake. So I'm suddenly failing geography right now. Lake Huron, sorry, and how Lake Huron, what's happening over Lake Huron affects what's happening over Lake Ontario. So right now, those are sort of the 2 venues people are looking for a correlation between. But certainly, yeah, how lake, sort of how the differential heating of lake happens. A lot of times what you get near the coast of these lakes is that's where the ice starts forming first. And that's not necessarily good for if you want a snowband. But then over sort of the middle of the lakes is where they're comparatively warmer and not ice covered.
We've got one of our listeners, Lloyd in New York, and he said he did participate as a CoCoRaHS participant in the Owls effort back in upstate New York there in 2013. So thanks for being part of that, Lloyd. Yeah. Really appreciate that. We got one more question we'll take just for time. Sean again writes, and he was wondering that if you participate in any research involving urban heat bubbles with the DAOs. So I'm not too familiar with that, but you might know something about that.
Right. So no, which is a fast, easy answer. But I'm not just I'm not just ending with that. I think there's going to be a project proposed looking at some of that, not by me. Again, I'd be a provider of the radar over Houston in the next couple of years. We haven't gotten the proposal yet, but there's been talk of using the radars to look at some of the urban heat island effect and aerosol effects in Houston in the summer.
Well, thank you, Karen. Again, appreciate your good stuff. I mean, there's a lot of interesting things here with winter coming on, and then the straight line winds, all kinds of stuff. So, a question for you: will you be at the AMS annual meeting in Boston? Maybe folks might be attending that and might run into you there.
Yeah, definitely. I hope to be there.
Okay,
I
so maybe
submitted
we'll see something
present,
from
but
you.
yeah.
Something there. That's great. Well, again, thank you. And it's been a pleasure having you back with us for a second time. As we close out our program today, we want to let you know that our next CoCoRaHS WxTalk webinar will be on wind energy. And that will feature meteorologist Greg Poulos, who's right down not too far away in Golden, Colorado from Karen. He's with Arc Vera Renewables, and this will be a very interesting a webinar. It'll be taking place on Thursday, December the 12th. So we'll have more information on our website for that. And then again, before I forget today, before you sign off or before we sign off, if you would take that brief survey that pops up on the screen. Appreciate that. So until we meet again, this is Henry Regis for the rest of the CoCoRaHS team saying goodbye for now and have a great afternoon.